the screen is yours.
Okay, so thank you so much for having me here today, and we have such a talented and interesting group of people here, and I hope the talk today will be interesting for all of you. Let me first share my screen. Okay. So, can you see my screen?
We can see it, but it's not in.
Is it now in the full screen mode?
Yes, it is. Thank you.
Sure. Okay. So the talk today is space level AI for monitoring infrastructure networks. And in a simpler word, it's a combination of AI and computer vision to better understand what's going on near power line or near electric grids or near transportation networks and any infrastructure in general. So a bit about myself. I'm Reza Arghandeh, originally from Iran, where I did my bachelor in electrical engineering and later in the University of Manchester, a master in energy systems, more into the mechanical engineering perspective and the energy conversion. And then I moved to the States, and in Virginia Tech, I got a PhD in electrical engineering, electrical and computer engineering, with more focus on the power system, electric grids, and also at the same time in industrial engineering, more focus on the operation research or optimization. And because I was so interested to use optimization and analytic for the electric grids. And after finishing the PhD, went to the other side of the US in the UC Berkeley, where I was a postdoc and was more specifically focused on data analytics, monitoring system, and machine learning for infrastructure networks, and again with a special focus on electric grids. And then I joined Florida State University as an assistant professor in 2015, where I founded the CI2 lab, which is the research group is specifically designed for developing and applying machine learning and AI algorithms for infrastructure network. And again, the core for our research is electric grids. 2018, I moved to the Norway here in Hovia, where I'm a full professor in AI and machine learning, and also leading the data science group. So the talk for today is mostly done with my PhD students, Michele Gazel, here in Bergen, with a close collaboration with my good friends and colleague, Dr. Eran Ozguban in Florida State University, and his PhD student Adijan. And it's supported by the European Space Agency and also with a close collaboration with the Tallahassee Commoner. So, well, the infrastructure networks are highly exposed to the climates and environments. And when we talk about infrastructure, basically we're talking about the electric grid, roadway, railway, pipeline, all this line that brings all different kind of commodity and support and service to our houses. So our life is highly depends on all this infrastructure, and the infrastructure are highly vulnerable to the environments and climate. And the problem is that in last decades, we were not happy, we were not keen to the mother nature. So we mess up with the climate, and it came back to us with all these extreme weather events we observed. And the first thing that damaged by any type of these extreme weather events are our infrastructures. And here are some examples of what we can see. So, if I want to talk about the monitoring, that's where the main pain is. Because, for example, just looking into electric grids, the amounts of lines we have, transmission and distribution lines we have in Europe, we have enough lines to go back and forth to the moon for 25 times. It's huge. And if we want to look into the roadways, we can wrap up the globe 1,600 times with all the roads we built so far. and to connect our communities together. So the problem is it's a huge scale. It's not easy to keep eye on them, and we need to monitor them. So the time and the cost is so heavy and so difficult to catch up with the scale of the infrastructure. Conventionally, we send a guy just walking and watching to the roads, to the lines, to the pipes, to the railway, or to drive a car or a bicycle or motorcycle, whatever. It's costly, it's time consuming. In some cases, we also use helicopters and some airplanes, which are much more costly and takes a lot of time. What can we do? Use a better technology like satellites, which brings a higher scale in a lower cost with a fraction of time, and also they are less prone to the weather and ground condition if we use, for example, radar technology. So what we observe today in a space industry is really a revolution. Compared to the 1957, there's the beginning of this space race or the space era. You can here see that in the bottom right, how the amounts of satellite launching the orbit increased exponentially, and this is even going higher and higher. If you see what's going to happen in the next 10 years or less than 10 years by 2030s, especially with having more and more private companies that came to the game, and they are daily launching a number of satellites to the orbit. So from the other side, the cost of launching of the satellite in the early days of the space era was maybe around $50,000 per kilogram of the loads of the satellites. And today, it's getting to closer to $100 per kilogram for the launching the satellite cost. What does it mean? It means that we will have, and we have, more and more satellite-based data with lower and lower costs and with a higher scale. Why don't we use it? So, moreover, the satellite data are not just a typical image we take with our phone or with our camera. They come with a different bandwidth, which means that with a different frequency, especially if we talk about the optical satellites image, and every bandwidth has a different type of information. So these satellites, in other words, these satellite data have huge amounts of information from different physical aspects or the biological aspects that we have on the Earth. And it's not easy for a human eye to analyze all of them. Human eye cannot compete with the amount of data, cannot compete with the frequency range or the bandwidth of this data we have. So we do need to have a help, and AI is a key here for us to decode all these satellites image. Another aspect maybe you are interested to know is the resolution of this image. So if you look at the image, for example, this one, top right, it's a Sentinel image with a 10 meter pixel, 10 meter resolution per pixel. It's for a switching or a substation for a grid. And you can see that with this resolution, we don't see much what's inside. We can just say that there are some trees around the specific area. When we switch to the planet with a 3 meter resolution, with a lower cost, we are more information. And when we switch to the high resolution satellite image with a 50 centimeter, we can basically start to see where are the trees, where are the towers, there's the switching, the transformer, and all the components in the switcher. The same for this kind of the railway. So by increasing the resolution, we see more and more information, but we have to pay more costs for that. And that's another trade-off we have. So that was a very short overview about the satellite's image and type of data we use. But in this specific case, monitoring the infrastructure network, one of the applications we are working is emergency management or assessment or the assessment of the impact of extreme weather events on the infrastructure before the events, which in this case is a storm, what I'm going to show you today, or post-storm, for vulnerability analysis and prevention in one side, to the damage assessment and recovery optimization on the other side. First use case for today is a post-storm assessment or recovery. This picture is from Hurricane Michael. in Tallahassee, Florida, 2018. And basically, this picture takes somewhere close to my house, where I used to live in Tallahassee. And for that specific hurricane, by the way, we've been out of electricity, out of water for a week, and in some part of the city for 2 weeks. So a lot of pain to the people. And that's the reason we are doing this study, to help people to suffer less after mass of the storm or hurricane in this case. So just to give you a better sense about this use case, Tallahassee is in the northwest of the Florida. This is the capital city. And for the Hurricane Michael, we acquired the satellite image pre and after the hurricane. And we basically start to look into what's the difference we see. We also collected some of the traffic camera data, the footage to compare, to cross-check with the satellite image, and here are 2 examples. The problem with the traffic camera is that they are not everywhere, and if you use the power or something, you may not get the video. And so satellite is basically more reliable and cheaper than the traffic camera or the ground-based camera. Okay, so we have the image from before and after the disasters. And what we do, the first step is we start to use some kind of machine learning algorithms to analyze, to understand the image. So for this case, for our methods, we use 3 different approaches to look into the image. The first one at the top is a tree segmentation block. And basically, we train our machine learning algorithm, in this case, a deep learning algorithm, to detect the trees before and after and look for the change. So if we see some kind of change in the tree profile near the roadways, we can understand that we have some broken trees or the broken branch on that. We also look at some filtering techniques. That's what's called NDVI. Basically, look at the frequency or the features that detects the amount of chlorophyll. I will talk about that in the next slide. But here is the overview. So 3 different methods come together. We do a voting scheme to decide, do we have a fallen tree in a very specific part of the road or not? And then we will give, as you will see, give this information to the municipality. So the first block is a tree segmentation block, which is a supervised approach to detect the trees. And the outcome of this block or this algorithm is what you can see in this short animation here. Basically, we tag the trees before and after the hurricane, and then we can measure the change. The second block is the normalized difference vegetation index. Basically, it's an indication of the amount of chlorophyll in plants, in vegetation at the surface level. And basically, it's more regarding to the near infrared or the red bandwidth in the image, because those bandwidths are more sensible or sensitive to the amount of chlorophyll. And what it can tell us where are the trees wherever we look at the image. And the last one is autoencoder based. It's basically unsupervised approach. The problem with the supervised approach is that we should have a human to sit, look at the image, and basically label the image and say that where is the tree, where is the road, where is the house, and then this process time consuming, need human, and also is costly. What we do instead, we can use this autoencoder, which are unsupervised, and automatically they can segment the image and they can group the image into the different groups like the trees, roads, houses. And when we combine all them together, we come up with this kind of a sweet spot between the supervised and unsupervised approach to reduce the computation time and to reduce the cost of analytics. So yeah, doing all these 3 methods, then we come up with this kind of histogram for each given area in the city. And in this use case, we are interested in the roadway because for us it's important where we have a fallen tree and where we have this roadway closure. Because we want to get people out of their home, or we want to send the lineman, go change, fix the lines. But if the road is closed, nobody can do anything. So that's the first level of the emergency response to clean up the roads and make the area accessible. Okay, so what we do, we come up with this histogram that can tell us, looking into the image, how can we decide where we have a fallen tree or the tree is okay. And okay, so here is a better slide to show you the result. 3 different layers in our machine learning. For the supervised, the NDVI, and the unsupervised, we come up with these maps for each method that shows where are the broken trees. And if 3 of these methods agree, then that's where we pinpoint as a broken tree or the fallen tree. You may ask how we are sure that our results are reliable or are correct or accurate. So for this hurricane, we collected the reports from the people who called the municipality and complained about the fallen trees. We also, in our collaboration with them, with the municipality, we also collect the data from their own inspection, ground-based inspection after the event, and we cross-check the location that the people and the municipality people pinpoint, and we compared with our approach, which came up automatically out of the satellite image, and we could see very good agreement between them. And here are more validation. Basically, we measure true positive, false positive, and false negative. And basically, if we really have a broken tree or we have an unbroken tree and we point it broken, so and compare our method with a different state-of-the-art machine learning algorithm, and we show that we got a very good accuracy compared to the classic approach. This is a paper that we published in IEEE Transaction on Industrial Informatics. Feel free to check that one. So that was post-storm use case. But the better question is that what can we do for the future extreme weather events or the future disaster, and how can we be ready? Because with this climate change, we will see more frequent events and in more unexpected times. So pre-storm assessment or preparedness, the way we define it, we calculate the vulnerability of the infrastructure based on the impact of the catastrophe. And in this case, we have a special focus on the vegetation multiplied by the vegetation exposure. In this case, vegetation exposure means tree density, tree height, tree health, and the impact of the broken tree or the fallen tree depends on the network topology, traffic amounts, the number of citizens who are going to be affected by this roadway closure. So here is the map of city of Tallahassee roadways, and by the way, the Tallahassee, maybe I didn't mention it, is a city of around 250,000 inhabitants. There are 2-3 universities there, and a lot of the government buildings. So in terms of size, it's similar to the Bergen in terms of the population, and it's mostly flat. So vulnerability function here relies on 2 or 3 major components: vegetation exposure, which I will explain each one of them in the next slide; building density as a proxy of the population who lives near the roadways; and the road importance, basically, which is what class is the road. We will see what are each one of these components. So vegetation exposure here, basically, we look at the satellite's image. We detect the tree. Where are the trees? How close are to the roads? And how tall are those trees? And what we do, we segment the roads to each piece of maybe 50 meter by 50 meter, and for each one of them, we measure the amounts of vegetation and basically the density of the vegetation, the size of the vegetation nearby the tree, and before and after the hurricane, we look at the change of vegetation density for any given points. And by looking at the differences, we can understand where we have some change, or basically where we have some broken trees. Here is a better closer looks under the hood. Basically, this is the deep learning methods we developed to estimate the height of trees. To estimate the height of trees, we use some LiDAR data that we had in the part of the city. We train our algorithms using these limited amounts of LiDAR data we had, and using that we could estimate the height of vegetation all around the city. And for the vegetation health, we use NDVI. That's the index you have seen in the previous application. And basically, we do the NDVI in a couple in a temporal way, in a different time span. If we look at the NDVI in a span of 1 year, we could say that if there is a dead tree, you don't see much change in the you don't see any vegetation growth, or you don't see much amounts of the chlorophyll in that specific tree. So it's a kind of NDVI is also a proxy of the health of the trees. And that was about the vegetation exposure. The next factor is the roadway importance for our vulnerability function. So in the US, we have three types of the road: national roads, which are basically the major highway that connects the different parts of the states together, the county road, like the regional roads, and the normal road, which basically owned by the municipality, and they are for the city. So we had that information we consider as one factor to calculate the road importance. We also use a graph theory metric between centrality and between different edges. So you know that in a graph that the nodes, the graph composed of the nodes and edge that connect those nodes together. And in our case, we translate this roadway network to a big graph with the different nodes and edge between each intersection, and we calculated this between centrality. And this is it's an indication of the travel time we need to go from point A to point B, having the different options to basically in these road networks to get from or origin to the destination. So we calculated this graph showed the amount of betweenness centrality for the whole city. And the other factor is buildings. So to calculate the building footprint, first of all, we can use some information which are available in the public domain, like this OpenStreetMaps. We have them for different cities, especially here in Norway, is accessible. So we can look into those kind of GIS database to capture the buildings footprints. And the buildings heights can also come up with some kind of LiDAR survey, which we usually have in each city. And similar to the method I show for the trees, we can also estimate the height of buildings from the satellite's image. So that's the one way. The other approach is that we don't have maybe any information regarding the building footprint. No problem. We can extract that directly from the satellite's image, and which we also did that as a practice. And we could extract and calculate the building footprints, and we know that near each roadway how many buildings we have and what are the size of that building, so on and so forth. Another important factor for us is the critical infrastructure, which means that hospitals, emergency shelters, firefighter station, the police station, and basically the emergency responder for that catastrophe or disaster. We also have the location for them, and we include that. So we put these type of roads, sorry, the size and the footprint of the building and the type of the buildings, plus this basically the graph theory metrics for centrality betweenness all together to come up with a metric that called roadway importance. So put everything together. Well, we have the satellite's image. And now remember, we are talking about vulnerability assessments before the disaster, before hurricane. So we look at just one single image to estimate this vulnerability. Also, we look at the temporal satellite image more for the health of the trees, plus the information, the GIS information we have from the roadways and the building data. So we bring this into our vegetation detection approach to model the vegetation and calculate vegetation exposure and health. That's one factor. Another factor, as I explained, this road importance, plus the volume of the building near the road, and put everything together, we come up with the vulnerability score. And we calculate this vulnerability score for any single piece of the roads in the city, and we come up with this kind of vulnerability map for the city. And here is the results. This vulnerability map shows that which part of the road, the blue means the more vulnerable and the red means red vulnerable. And we could see that the roads ended to this kind of the city center with the most critical infrastructure there, and the highways have more vulnerability because if they close, more people will be affected. And this kind of maps helps people in the roadway authority, in the commune, and the people who are the emergency responder to know where they need to put more attention, maybe to do a better vegetation management, or to launch more, or to dispatch more the ambulance or the storm responder vehicles around that area, or put more and more responder in that location, and basically help them to better plan for the next extreme weather event. I almost done. Here are some publications out of this research, which you can check them, and more information regarding what I presented today is available in these papers. Thank you. That's for the presentation. I hope I was on time.
Thank you, Reza.